Hello, everyone. Today, what we're going to do is finish up on minimum spanning trees, looking at Prim's algorithm, and then get started on shortest paths and look at one of the most famous algorithms in computer science, which is Dijkstra's shortest path algorithm. I like to do these two algorithms in the same lecture because they have a lot of similarities. So let me start by reminding you what minimum spanning trees are. We have an undirected graph and we have weights on the edges. And what we're looking for is amongst all those weights, how can I take a minimum weight subset that connects the vertices? So we, here were some examples that we looked at last day for this little graph. If I take this subset of edges, it indeed connects everything together and with weight 7. This tree connects everything and has weight 10. And here is the minimum weight spanning tree of weight just 4. So one of the things we discussed last day is that the set of edges will be a tree always. There's never any reason to include a cycle in such a minimum weight set of edges, so long as the weights are non-negative. Okay? And the other thing we looked at last day was Kruskal's algorithm to find a minimum weight spanning tree. And what I'd like to start with today then is to look at an alternative algorithm called Prim's algorithm. Okay, so here is what Prim's algorithm does. We grow one connected component in a greedy fashion. So it's an alternative greedy algorithm, rather different from Kruskal's. So the general structure is that I start at some arbitrary vertex S, and I grow a connected component that includes S. So at a general point in time, C will be the set of vertices that I've reached so far. And I have various other vertices that I haven't reached yet, and some edges cross from the set C to the vertices I haven't reached yet. And we are greedy in the sense that we pick the minimum weight edge that crosses from C to a vertex not in C. So we choose this minimum weight edge, leaving C at each step. So here's how we would do this. We initialize the set C to contain just the vertex S. Again, S is an arbitrary vertex. Our tree is initialized to be the empty set. And while I have not reached all the vertices, I find a minimum weight edge E that has one endpoint in the set C and the other endpoint not in C. I add that edge to my tree, and I add that vertex V to my set C. Now, as far as correctness of this, the exact same exchange argument that we looked at last day for Kruskal will also work, and I'm not going to go through the details of it. Now, it is in fact true that you can prove one single lemma that proves simultaneously the correctness of Prim's algorithm and of Kruskal's algorithm. You can find that proof in your textbook, CLRS. I didn't choose to do that because I think it's much easier to understand if you're just focusing on one algorithm first. So that was why I didn't present you with that really general proof. Okay, so let's move on and talk about how we would implement Prim's algorithm and analyze the runtime. So again, we are doing this on a word RAM model, which is we're assuming that each weight fits in one word, and we can add them up and compare them and so on, do basic arithmetic at unit cost per arithmetic step. We analyze things in terms of the number of vertices and the number of edges. So again, here's the algorithm just so we can refer to it. And this general step is that I need to find the minimum weight edge that leaves the set C. And the natural thing you should think of for that is, oh, I need to repeatedly find the minimum in some set that's sort of changing out from under me. So a priority queue is the right data structure for that. So we want to have the operations available to us of finding and deleting the minimum weight, because that's what we're doing here in this step. And then the update operations that are allowed for a priority queue are insertions and deletions in the set. So priority queues, as you know, can be implemented as a heap. You've seen that in CS240. And the time it takes for each of these three possible operations is then log k, where k is the number of elements in the priority queue. The maximum number at any time, or you can think of k as when I perform an operation, how many things are there in the set? And then k changes out from under you. Now, in our case, the current set of elements, here's a piece of notation for you. It's the set of edges that leave the set of vertices C, and we call that delta of C. It's sort of the boundary of C. Now, what that means is that our value of k is bounded by m, the total number of edges. So then we are looking at a log of m time for each of the priority queue operations. Now, the elementary things we must do then inside Prim's algorithm is find the minimum weight edge that's in our boundary set, delta of C. So that's a find min operation. And then we need to see, well, how do I update that set of boundary edges when the vertex V is added to the set C? So we're going to look at that a little more carefully and then sort of put things together and say, how many of each of these operations am I doing? All right, so here again is the general picture of what we're looking at in Prim's algorithm. We have a current set C, and I'm supposing here that V is the vertex that I find that I am going to add to the set C. And how am I going to update this boundary set? So let me see. The current boundary set is, let me perhaps draw it in blue. This is my current boundary set. This is the edges leaving the set C. And what I want to update it to is now this set. So this is the new delta of C. All right, because the vertex V joins C. So the edges that have to leave my boundary set are these ones. Okay, so the edges that go between C and the vertex V are the ones that leave my boundary set. And so I use delete operations to get rid of those from my current priority queue. And on the other hand, the edges that are the other edges incident to V, and I wish I had a third color, but I don't. So let me draw these with squiggly lines. The other edges incident to V, and that would be these ones. They are the ones that join the boundary set. They're part of the new boundary set. And for those, we're going to use insert operations. Okay. Now, how do I find all of these edges, these ones and these ones? What I do is go through V's adjacency list, because every edge incident to V either leaves the boundary set or joins the boundary set. And how do I know which? I know which by testing the other endpoint to see, is it currently in the set C or not? Okay, so I go through V's adjacency list once. And then the thing to observe for the runtime is that each edge will enter this boundary set once, and it will leave the boundary set once. So per edge, how many insertions am I doing? One. And how many deletions am I doing? Just one. So with that in mind, we can analyze the runtime here. The time per operation, we were saying this is going to be order log of the size of the priority queue. And that's the number of edges at worst, at the maximum. How many times do I do a find min operation? I do that until C contains all the vertices. So I'm doing it n-1 times, once for each vertex other than S, which started in C in the first place, right? And the number of insert and delete, well, as I mentioned, we do one insert per edge and one delete per edge. So the total runtime then is going to be order n, this is for the number of finds, times log m per operation. So this is the find min. And plus my inserts and deletes, there are m of them. and each one costs log of the size of the priority queue. And altogether, this is, so I should write here, sorry. I should write that these are for the inserts and deletes. And altogether, this is giving us a runtime of order m log n. Remember, because m is at worst n squared, and log of n squared is 2 log n. And the other thing I've done in this final line is say, oh, I have here an n log of m and here an m log of m. And here I'm assuming then that m is at least n. The reason we can make that assumption is because we don't even need to run a minimum spanning tree algorithm if there are fewer than n-1 edges. Okay. So that completes, this is the final runtime then of Prim's algorithm. We're getting the same runtime as we did with Kruskal's algorithm. We are using perhaps a more basic data structure, just a priority queue data structure. Whereas if you remember for Kruskal's algorithm, we needed the union find data structure, which was not something I think that you did in CS240. It's not so basic. Okay, now there's two comments I want to make. One is that it is slightly more efficient to keep a priority queue of the vertices that are outside C. So these vertices over here. And the point is that then the priority queue has size n at the most, whereas with the way we're doing it, keeping edges in the priority queue, the size of the priority queue can be as bad as n squared. So this is why I say slightly more efficient. It doesn't change the asymptotic runtime, but it does change things in practice because the priority queue is smaller. So how can we do it by keeping a priority queue of these not yet added vertices? The idea is that we set the weight of a vertex to be the minimum weight of an edge that goes from the set C to the vertex V. So that's what we would have to take into account. Okay, what are the different possible edges that go into a vertex and which one gives me the minimum here? The update operation then becomes a decrease key operation. Perhaps that's an operation you studied in CS240. That also takes order log n if you implement the priority queue as a heap. One way to do it, a decrease key, is to remove the element whose key is changing and then insert it with the new key value. So we're doing 2 log n time operations. But for some implementations of a priority queue, the decrease key can be done even faster than this. You shouldn't do a delete and an insert. There's a faster way to do it. With a heap, I guess the way that you can do it, if you remember how a heap works, we're decreasing the key of an element so it would sort of bubble up in the heap closer towards the root. The root is storing the minimum value element. Altogether, this still gives m log n total, but if you look up Prim's algorithm anywhere online, you're going to find this slightly more efficient method. I presented it using the edges because I think it's easier to understand that way as a first presentation. And the one last thing I will add here is that the fastest way to implement Prim's algorithm is to use a different way of implementing priority queues. So a Fibonacci heap, this is the name of the fancier implementation of a priority queue. Gives a total runtime that's better because with a Fibonacci heap, you can do a decrease key in order 1. So the total time that we get then is going to be n log n. This is because I'm doing still my n-1 find operations, each at log n. But my changes to the priority queue are just decrease key operations and m in total. So this is theoretically better, In practice, I think it's better to stick with the ordinary heaps that you know, because Fibonacci heaps are very complicated. But from a theoretical point of view, this is the best way to implement minimum spanning trees. Okay, so here's a summary of what we've done so far. Prim's algorithm for minimum spanning tree. It is a greedy algorithm, but different from Kruskal's greedy algorithm. And what you should know is what is Prim's algorithm, how to implement it, and what runtime we get. Never mind the Fibonacci heaps, that was just sort of added information. What we're turning to next is shortest path algorithms. So new topic, new problem, but we're going to look at an algorithm that is slightly similar to Prim's. All right, so we're looking for the rest of this lecture and also for the following lecture at shortest path problems in edge-weighted graphs. So this is an incredibly practical problem. We have a road network. We want to know what's the shortest route to travel from point A to point B. Or we have a network and we want to know the fastest way to route a message from one point to another. Very, very practical problem. Now, the one way in which we've seen this problem so far in this course is that we saw that a breadth-first search, if we started at a particular vertex V, then it's going to find the shortest paths from V to all the vertices in an unweighted, undirected graph. So unweighted means I just count every edge as weight 1. I'm just counting how many edges are in the path. So specific for unweighted and undirected, we know how to do this in linear time. Now, more generally, we're going to have either a directed or undirected graph. We'll look at algorithms for both of these, and we're going to have non-negative weights on the edges and sometimes maybe negative weights. Okay, so there's going to be a variety of different scenarios that we'll look at. So just a basic example to show what shortest paths mean in a weighted graph. If I look at this example and I say that I want to get from vertex A to vertex D over here, well, there's various possibilities. I can do it with just 2 edges, but then the weight is 5 plus 2 or 7. That's a pretty heavy weight path. A better way might be 3 plus 1 plus 2. So that would be weight 6. And 3, 4, 5 this way, or 3, 4, 5 this way. So there are ties for the shortest path, but the weight of it is 5. And let's write down one of those possibilities. So A to B to D of weight 3 plus 2 equals 5. If there are multiple paths of the same weight, we might prefer the one that has the fewest edges. And that might be one of the things we'll look at in maybe one of the problem sets. On the other hand, if I look, for example, what is the shortest path from A to E, I could get there with weight 5. I could also do weight 3 plus 1, and I believe that's going to be the shortest here. So A comma B comma E of weight 4. Okay. Now, we were just doing minimum spanning trees. So one thing you might wonder is, does a minimum weight spanning tree always contain shortest paths? And the answer, even for this little graph here, you can see it, the answer is no in general. No, not always. And another thing we might consider is, since we know how to find shortest paths if all the edges count for 1, all the edge weights are 1, could I reduce the current problem when there are edge weights to that unweighted case? And you might think when the edge weights are integers, like they are here, that we could do that, right? So maybe I have an edge of weight 3, and what I would change it into is 3 edges in a row, so that now if I traverse this, it costs me 3. So think about that. This is indeed a correct reduction. But what is the runtime? Here we've taken the number 3, which we can express with log of 3 bits, and we've changed it into the number 3 in unary. I've changed it into 3 edges. Okay, so the issue is that this is not polynomial, not a good running time. I know we haven't talked very formally. I know Professor Brown mentioned this, but we're going to talk a lot more about what is polynomial runtime. And this is not a case of getting a good runtime. If I had an edge weight of 100, instead of doing on a word RAM my unit cost operations on 100, I would be changing that into 100 weight 1 edges and taking time proportional to the number 100 rather than log of 100. Okay, so let's move on to some good shortest path algorithms. We're going to study directed, undirected graphs, single source, all pairs, and I guess I should add here non-negative or arbitrary edge weights. Okay, and the algorithm that we're going to look at first is Dijkstra's algorithm. So this is an algorithm that comes from way back in 1959, and I'll tell you a little bit of the history of why Dijkstra invented this algorithm back then. But let's first look at what the algorithm does. So it works on either a graph or a digraph. And the edge weights, on the other hand, have to be non-negative for this algorithm to work. That's going to be important. We are starting with a start vertex S, and what the algorithm finds is the shortest path from S to every other vertex. Okay, so this is called a single source shortest path algorithm. It presumes that you know your starting point, but you're going to answer it for every possible end point. Okay, and then just to be a little more precise than I was on the previous slide, what does a shortest path mean? It's the path of minimum weight. And what does that mean? What is the weight of the path? It's the sum of the weights of the edges in the path. Okay, so just to be precise about that. And one more point is, how do we give the output? I've suggested that we should have the shortest path from S to every other vertex. There are n-1 other vertices, and each of those paths might have n edges. So you might think that we are asking here for order n squared size output. And that's not the case. We can get by with an output of size order n. And the way to do that is to discover or prove that the set of shortest paths can be captured with a tree. And that's going to come out of Dijkstra's algorithm. Okay, so what is the idea of Dijkstra's algorithm? It's to grow the tree of shortest paths starting from vertex S. So this picture is going to look exactly like Prim. So that's what I was saying. There's some similarities between this and Prim's algorithm. So, and I've drawn it as a directed graph, but this algorithm works for directed or undirected. So starting from S, and initially I would have only S in my set of reachable vertices, I grow this shortest path tree so that at any point in time, I know what is the shortest path to every vertex in my set B, okay? And at each point, I want to grow my set B by adding one more vertex to it. So I'm going to be looking again at the boundary of the set B, namely the edges that leave the set B, and I want to see which edge should I add so that I have the shortest path to one more vertex Y, and then I add that vertex Y into my set B. So it is again a greedy algorithm. We have to be a little careful what we're being greedy about. Remember, in Prim's algorithm, we were just looking at the weight of this edge. Here we have a different problem. We are looking for shortest paths from S to the vertex. So our objective will be different. So again, just a little more in words, we have the tree of shortest paths to all the vertices in the set B. And initially B is just S. We are going to choose one new edge. Here it's shown as the edge X to Y, where X is in my set B and Y is outside that set. And the thing I would like to minimize, to be greedy about, if you like, is the distance from S to that start vertex X plus the weight of the edge from X to Y. Okay, so I am considering all the ways I can get from S to some vertex in B and take one edge to the vertex Y. And out of those various possibilities, I'm picking the shortest path that does that. So I'm minimizing over all possible pairs XY, satisfying this. I'm minimizing the distance from S to X, which is something I know already because X is in B, plus the weight of the one new edge that goes outside B to vertex Y. I'm going to call that number D for now, okay? And then the update I need to do is I'm going to then declare, oh, the shortest distance from S to Y is the value D. I will add the edge XY to my tree. In other words, I will say, oh, if I want to get to Y, I should first get to X and then take the edge XY. I set the parent of Y to be X, and I add the vertex Y to the set B. So these are the updates that I do. I'll give you the exact pseudocode in a moment. What I'd like to address first is just the idea of this and why should this be correct. So again, it's a greedy algorithm in the sense that we're always adding the vertex, namely Y here, that has the next smallest distance from S. And that's actually something we need to, that's not true without the proof. We need the, I mean, it is true, but we don't know it's true without proving it, okay? So the claim here, the correctness claim is that this value D here, maybe let me circle, this D is this D, just so it's clear. This D is the minimum distance from S to Y. That is, no matter how I travel in this graph, travel here, travel out there, whatever kind of path I take to Y, it is going to be at least as long as the value D. D is the minimum distance. So let's look at the proof of that claim. So again, the scenario we're in here is that we're assuming that the distance from S to X is correct for all X in the set B. And then we define D like on the previous slide. And then the claim is that that value D is the minimum distance from S to the vertex Y. Okay, so we want to show that for any path, from S to Y, so this is to prove, any path from S to Y has weight greater than or equal to D. Okay, that'll show that D is the minimum distance from S to Y. So consider such a path. Any path from S to Y. And let me call that path pi, standing for path. And I'm going to break this up. Break up the path pi into the following. Let me draw a picture of this. So I have my set B, and I have S. I have my vertex Y, which is currently outside here. And I'm going to say, okay, I have some path that goes from S to Y. It might wander around in here for a while. I'm not saying it has to be part of the tree, just that it wanders around here for a while. Eventually, it has to take an edge that goes outside the set B, right? So it goes from some vertex U to some vertex V over here. And then maybe it wanders around, maybe it even goes back into the set B, and eventually it gets to Y, okay? So B in blue was my set B. Okay, so I'm going to break pi into pi1 is the initial part. That stays inside the set B. Okay, so in this picture, pi1 is the part that goes from S to U. S to U, staying inside B. Then the path has to have some edge that steps outside B, right? So the E equals the edge from U to V, the first edge of the path of pi, leaving B, just like in the picture. And pi2 is the rest of the path. Okay. So what is the weight of my whole path pi? Well, I've just broken it into 3 parts, right? So it's the weight of pi1 plus the weight of that edge E plus the weight of the remaining part. And I want to first say that I can ignore the weight of the remaining part. I am trying to show that the weight of this path is at least D, right? So here I'm saying it's greater than or equal to, and I'm just going to take the weight of pi1 plus the weight of E. Well, why is this true? It depends very much that the edge weights are greater than or equal to 0. Okay, so this is because edge weights are greater than or equal to 0. And this means that the weight of pi2 is greater than or equal to 0. Okay, this would fail if we had negative weight edges. All right, and then the next thing I want to claim is that this is at least the distance from S to U. Why is that? So this part I'm claiming is greater than or equal to this part. I have some path from S to the vertex U, and I knew that I have the correct shortest paths already stored in my D values. So the weight of this path is at least the minimum weight path, which is the distance from S to U. And I'm leaving the other part alone, the weight of E. Okay. And then I just want to say that, well, I chose my, my value D to be the minimum of anything of this form, the distance from S to some vertex in B plus the weight of a single edge leaving. Okay, now I get to the vertex V here, but if let's look back for just a second, I chose this edge not for a specific Y, but I chose it over all possible values of the vertex Y to minimize this quantity. So here I have something that is of the form of what I was minimizing on the previous slide, and I chose D to be the absolute min here. Okay, so let me write down the reasons for these steps. So this is because U is in B. So we have the minimum distance, the D value. Let me not mix that up with the other D I'm writing. D of SU is less than or equal to the weight of any path going from S to U. And this step here is because we chose D to be the minimum. Okay. And what this means, therefore, once we've proved this claim, this is the end of the proof of the claim, is that by induction on the size of my set B, this algorithm will correctly find the minimum distance from our given start vertex S to every other vertex V. And yeah, so this gives us the length of a shortest path. If I actually want to find the path, then I'm going to follow my parent pointers backwards from V until I get back to S. Okay, so here is I guess I would like to say a little bit about implementation before I describe the pseudocode that uses this implementation. So if you remember then, our plan is that we're choosing one edge, leaving the set B to minimize this. This is what I was calling D. And as for Prim's algorithm, if I want to implement this, I can use a priority queue, in other words, implement it as a heap, if you like, where the elements are the edges that leave the set B. So the edges that are in delta of B, using the notation we had before. And now, rather than just saying the key or the value of an element in my priority queue of an edge is the weight of the edge. In this case, it's different. The value or the key of an edge is the distance from S to the first vertex of the edge plus the weight of the edge. Okay. Now, as for Prim's algorithm, it's more efficient if I keep a heap of the vertices. It does not change the asymptotic runtime, but it does, in practice, it's more efficient to have a heap of size n than a heap of size m, which might be n squared. Okay, so now we want to make a priority queue or a heap on the vertices that lie outside of B and set the key value of every vertex to be, we can think of it as the tentative distance, which is the minimum weight of a path that goes from S to Y, but that has this special form that I start from S, I follow tree edges to some vertex. And then I look at one possible edge going out of that. So I will compare for any vertex Y outside B, what are all the possible ways that I could travel from S inside the set B to some vertex in B using the shortest path then, and then take one edge stepping outside. Okay. So this is the definition of D of Y that I store alongside the vertex Y and use as my key values in the heap. Okay, so with all of that, here is Dijkstra's algorithm, how the way it works. I initialize the tentative distance to any vertex being infinity. So far, I can't get to that vertex at all. I update the distance to S as 0 because I'm already at S. S is my starting vertex. I initialize B to be the null set in this case. Note, I'm not putting S into it right away, okay? And I set up a heap on all the vertices V using those tentative distances here as the key values. Now, while my set B is not the whole set of vertices, I pick a vertex of V minus B that has the minimum D value. In the very first step, what is this going to do? It's going to pick my vertex S. So the very first choice for Y will be the vertex S itself. More generally, I'm using my priority queue and doing a find min operation. Now, the tricky thing is that I need to then update the values that are attached to the vertices outside B. And the way I do that is I'm considering my set B is going to grow to join Y. So for every edge that goes from Y to some other vertex, like a vertex Z, I need to update and say, oh, I now have a new way to travel to vertex Z, starting from S. I can take a path inside B to Y and then take one edge outside. So I have to do that update. So if the distance to Y, which, that just came from my heap, plus the weight of the edge from Y to Z is less than the current value I'm storing for Z, then I do an update. I set D of Z to be this improved value I've just found, this shorter, smaller value, and I update the heap. So the key value of vertex Z has decreased. And then I set the parent of Z to be equal to Y. And that's so that I can trace back with my shortest path. By the way, note that when I added this vertex into B, which I guess I should have added in here. So I should have one more line in here that says add Y to B. Okay. I don't need to set its parent there because I will have set its parent along with its tentative distance as I go through the algorithm. Okay, so here's that same code here, and we'd like to talk about what is the runtime of this. The correctness is what I already proved, that by finding this minimum, we're doing the correct thing. So we've got a priority queue implemented as a heap on order n elements. Find, min, insert, and delete all take log n time. And how do I update the heap? The value or key of vertex z changes for all the neighbors z of y. And I can do that by deleting and reinserting z, or I could use a decrease key operation. Either way, with a heap, it's going to cost me log n to do that. So the runtime that I'm getting then, I have my n-1 find operations because I'm adding vertices one by one. I guess actually in this case I have n because the very first find finds the vertex s. And then every edge causes me to do possibly one insert and delete or one decrease key operation. So the total time is then going to be the same as it was for Prim's algorithm. This is the number of find min, log n per operation, plus order m log m n. Now we are explicitly making a heap of size n. And this is for the inserts and deletes, or the decrease key, if you like. And the total here then becomes order m log n, assuming m is at least n. Okay. So that's our total runtime then for Dijkstra's algorithm. And the one last thing I wanted to tell you was a little bit of the history. I have a picture of Dijkstra from the time in the 1950s when he discovered this algorithm. He was known not only for this algorithm, but for many contributions in computer science, concurrent programming, structured programming. This shortest path algorithm, he designed it for a slightly strange reason. He had some hardware that he wanted to demonstrate the capabilities of. So he had an audience of people who were not familiar, especially back in the 50s, with computers at all. And he wanted to demonstrate that a computer was a useful thing. So he used the shortest path algorithm to find how to get the best railway trip in the Netherlands between any city and any other city, and designed the algorithm for that reason. Now, at that time, the result was not considered like an important discovery in computer science. Computer science altogether was in its infancy, and the analysis of algorithms was maybe in pre-infancy. And what Dijkstra wrote about it later on, I think, he said, at that time, algorithms were hardly considered a scientific topic. I wouldn't have known where to even publish it. The math culture of the day was very much identified with the continuum and with infinity. Could a finite discrete problem be of any interest? The number of paths from here to there on a finite graph is finite. Each path is of finite length. You must search for the minimum of a finite set, and any finite set has a minimum. Next problem, please. It was not considered mathematically respectable. So in terms of the history of mathematics, calculus is what has been done for some centuries. People were interested in continuous problems and how to analyze trajectories of cannonballs and, you know, the rate at which water fills vessels and things like that. And finite problems, discrete problems, were considered too small to be interesting. That's what Dijkstra is essentially saying here. And it's only with the advent of computers and the world the way it is now, airline schedules and routing problems in huge networks, that discrete problems are considered extremely interesting. And the runtime of algorithms as a function of that discrete size is considered incredibly important. So anyway, Dijkstra was at the very forefront of that. And I think this little bit of history of the reason he discovered this algorithm, which was just to show the usefulness of some hardware, I think that's pretty interesting. Okay, so a summary of this lecture: we looked at Prim's minimum spanning tree algorithm, and we looked at Dijkstra's shortest path algorithm. You should know what is Prim's algorithm, how to implement it, and what is the runtime, and the same thing for Dijkstra. You should certainly know the conditions for Dijkstra to work. Does it work on a directed graph, an undirected graph? Does it assume we know the start vertex? Does it assume we know the end vertex? Is there any property that's required on the weights? Yeah, the weights have to be non-negative, okay? And it's also good to think through again the differences between Prim and Dijkstra. They are both greedy algorithms, but the objective function that we are being greedy about at each step in the algorithm differs. And next, we're going to look at some more algorithms for shortest paths, but that's it for this lecture.